So what I'm going to do is I'm going to put on a timer, and when that goes up, everybody will hold up their answers, all right? Try to make it a little bit less chaotic. I'm going to put on a timer, and then you'll hold up your answer. All right, let's see them. Who's got it? So the correct answer would be 3.747 moles of carbon to the correct number of sig figs. Boom, like it. Okay, so what do I need in order to convert from grams to moles? Molar mass. So I got to look on the periodic table. For carbon, the molar mass is 12.0107. So I'm going to start with what I have, my 45.00 grams of carbon. And am I going to be multiplying or dividing by that molar mass? I need to divide so that grams are on the bottom. Punch that into my calculator. My units are moles of carbon. And importantly, I should have 4 sig figs. So that's how I get my final answer here. Okay? All right, so team in the back, where are we going next? Covalent 400, going big here, huh? You're going to give me the name of the compound I gave you the formula for, and you're going to give me the formula for the compound that you have the name of. So 2 questions in one here. So you're going to give me the name of the compound that you have the formula for, and you're going to give me the formula for the compound you have the name of. Sure. I don't know how well they can race at this point. Some of them are pretty gunked up, but yeah.
What are we doing next?
Just answering these questions. Yeah. 8 seconds. 8 seconds to finish it up. All right, let's see it. Okay, so the first one would be tetraphosphorus, right? Don't put the "ide" on the end of the first one. And then oxide. And then octanitrogen heptaoxide. Octa is 8 and hepta is 7. Hept is one that a lot of people forget for whatever reason. Okay, so just make sure to file that away. All right. Who got it right? Let's see. Awesome. All right, Frosty in the back here. Pick the next one for us.
Metric or treat for 100.
Metric or treat for 100. 4,300 meters to kilometers. All right, does anybody have it? All right, 4.3 kilometers. Okay, so if we look on our constants page and we find kilo, it's like kilo, K, and 10 to the 3. Remember, we got to know how to read that piece of information. Some amount of kilometers equals some amount of meters. Where does the 1 go? With the prefix. So 1 kilometer is 10 to the 3 meters. That's how we read that constants page. So then we're going to use that piece of information, starting out with our 4,300 meters. We're then going to use the fact that there are 10 to the 3 meters in 1 kilometer. So we're going to punch that into our calculator, and our calculator gives us 4.3. 4.3 is the correct number of sig figs because there's no decimal in this number here. So this only has 2 sig figs. So my final answer is 4.3, kilometers. All right. Sarah, give me the next one. The big unit for 100. So these are going to be unit conversions. I want you to convert 230 inches into centimeters. Always. Always rounding to the correct number of sig figs. All right, so let's see who's got it. Sig figs. So the correct answer is 580 centimeters. There's no decimal in this number, meaning it only has 2 sig figs. So starting out with what's given, 230 inches, I'm then going to look on my constants page and find my inches to centimeters conversion factor. That tells me that 1 inch is 2.54 centimeters. I punch that into my calculator, I get 584.2. My units would be centimeters, but then I have to round to the second sig fig here. What you want to make sure not to do is say 58, because 584.2 rounded is not going to be 58. That's a completely different number, so you have to have that 0 on the end. What's up?
I have a question, because when I was doing the Alex objectives, how does write it in scientific notation?
So
5.8 times 10 to the second.
That'd be perfectly fine. Yeah, and that's an Alex specific rule, so I don't care if you do that on an exam, but you absolutely can. That's the exact same number. 5.8 times 10 squared is the exact same number as that. So I'd be cool with that. All right, Edgar, let's get our new category. What's it gonna be? What is it, ions? For what, 500? Holy cow, all right, let's do it. First big one. You're gonna give me the name of this compound here and the formula for the second one. Give you all a hint. Yttrium would be element 39 there. Nice job. All right, so this is the 500 one, right? This is like worst case scenario here. We have our transition metals and these polyatomic ions. So first of all, what is PO4 minus 3? Phosphate. And so what is the ones that end in ite? One less oxygen, right? So if phosphate is PO4 3 minus, this would be PO3 3 minus. That is a phosphite ion. So when I'm doing my formulas, remember you're going to start with the ions, each ion and their charges. Yttrium 6 means that there's a +6 charge. And then what I'm going to do with these charges? Cross, right? So this becomes Y3. And how do I indicate that I have more than one polyatomic ion? Parentheses. So PO3, 6. And then am I done? I got to do one more step because this is an ionic compound. Remember, only with ionic compounds are we going to then reduce our formula. So this will be YPO3, 3. I mean 2. It's Friday, sorry. All right. So then for the other one, this is SO3. What's SO3? Sulfite, right? Because SO4 is sulfate. And then we got titanium. Titanium lives where on the periodic table? Transition metals. So maybe this was a little bit of a hint, but you have to include the Roman numerals. So I'm going to have to first figure out the charge on that titanium ion. And I'm going to use the fact that there are 2 sulfite ions, each with a charge of -2. So that's a total amount of negative charge of -4. So then what's the charge on that titanium? It's got to be +4. So this would be titanium 4 sulfite, right? The 8s and the ites are our polyatomic ions. All right, let's go. So pick another one for me. Isodope for 500. Got big money going now here. All right, so all of the vanadium on Earth is found in one of 2 stable isotopes. Vanadium 50, which has that mass, has an abundance of just 2.50%, while vanadium 51 accounts for the remainder of the vanadium on Earth. What is the average atomic mass of vanadium? All right, and you're just going to round to 3 decimal places. All right, anybody got it? Nice. All right, 50.919. Be careful, I told you to round to 3 decimal places. And then the units are AMU. So these are these average atomic mass calculations, right? So the average atomic mass is the percent of isotope 1 divided by 100 times the AMU of isotope 1 times the percent of isotope 2 divided by 100 times the AMU of isotope 2. All right, so I'm going to do the percent of this first isotope divided by 100 times this mass. And then how do I get the percent of the second isotope? Because that's not explicitly given. I told you all the rest of it is that second isotope. So that means 2.5 plus what is going to get you to 100%? And that would be 97.5. So I would take that 97.5, divide it by 100, and then multiply it by this mass here. Okay, so just to be clear, I'll set it up. Nope, 964. Right, punch that into my calculator and I get my 50.919. Again, percent of isotope 1 divided by 100 times the mass of isotope 1 plus the percent of isotope 2 divided by 100 times the mass of isotope 2. All right, Percy, let's get the next one here. Covalent schmovalent for 500. Yeah, all of a sudden, not messing around here. Yeah, well, I think we might be. Yeah. All right, who's got it? Let's see it. Okay, so the bottom one, a lot of people are getting correctly. Nana is probably one of the lesser known, or one of the more rare prefixes to use here, but Nana is what?
9.
So this would be BR9, and then hexa is, so F6. Now, for this next one, a lot of people are falling into this very easy trap to fall into. We're getting the first one right, tetra. Iodine, not iodide, right? Because we only put the IDE on the second one. But for this next one, the second element always needs a prefix. So it is not just nitride, it is mononitride. Tetraiodine mononitride. Right? You got to include a prefix on that second element, even if there's only one of them. All right, Dahlia, let's do the next one.
Metric for 500.
Metric for 500, all right. Not messing around. For 7.4500 times 10 to the negative 14 megajoules into microjoules. Close. What's that last step? What's that last step? There it is. Yeah. And I did find you can get the larger one, this large black one, will work well, and then I'll take this eraser. There it is. Other way. I think you're flipping where the 10 tubes need to be. Oh, unless maybe you did positive 14 instead of negative 14. I don't know. But yeah, you're going to get a small number, not a big number. No? Oh, okay. Then I thought I grabbed the new ones, or some new ones at least. Yep. Yeah, unfortunately. I'll just keep trying. Yeah. All right, 0.074500 microjoules. Okay, so how the heck do we get that? So first of all, I'm going to have to look up two of my metric prefix conversions here, right? Because I have two prefixes, the mega and the micro. So I get 1 megajoule equals 10 to the 6 joules, and 1 microjoule equals 10 to the negative 6 joules. That's what I get from my constants page. Again, the 1 goes before the prefix. That's the one double check you always want to have in your head. Make sure you're putting the 1 in front of the prefix. So then I'm going to set this up with what's given, 7.4500 times 10 to the negative 14 megajoules. So then I'm going to need to put megajoules on the bottom. If I stopped there, I'd convert from megajoules to joules, but it wants me to go one step further and convert to microjoules. So then I'm going to divide by the 10 to the negative 6 joules equals 1 microjoule. I punch that into my calculator and it says 0.0745. My units would be microjoules, but then I need to make sure to go back and do my sig figs. 7.4500 has 5 sig figs, so I'm going to need to tack 2 extra zeros onto the end there. All right. Who hasn't picked one? Wendy, pick one for us. For 100? Okay. Again, complete the rest of this isotope table for me. All right, and I'm going to give you all a minute to fill this out. Yep. All right, so let me see it if I have not already. All right, not -1. So actually everything that we need is in this symbol right here, right? Because that 108, that top left corner, that's my mass number. That bottom left corner, that's just the atomic number, the number of protons. And that top right corner is the charge. All right, I think the hardest part of this one would have been hunting on your periodic table to figure out what the heck Ag is. And Ag is silver. So silver 108. That's how I would finish off this table here. All right, Gil, pick the next one for us.
Ion for 200.
Ions for 200. Oh, bummer. Whatever. Mm-hmm. They're not the exact same, but they both have selenide in them, so that wasn't the smartest choice. Here, I lied. I'm going to change it. Do that one. Is that ID? Sulfide. Yeah. ID? Yeah. Your formula needs work. Sarah, formula. Look at the charges. You're good. Yep. There it is. The formula needs work. That one's good. Yeah. All right, so the name would be calcium sulfide. So two things I want to put up on the board here so we can see them all next to each other. We have an S all by itself with a 2 minus, an SO4 with the 2 minus, and an SO3 with the 2 minus. When it's all by itself, it has what ending? IDE. So this is my sulfide. This one is the sulfate, and this one is the sulfite. So just be careful about these endings here, right? That's what you want to pay careful attention to. In this case, it would be calcium sulfide. When I'm putting my formulas together, again, remember, do it the long way. Put down each ion. Cesium with a +1 charge. Selenide is selenium with a -2 charge. So then I do my cross and I get CS2Se for cesium selenide. All right, Bernard, give us another one.
Metric or treat 400.
400, all right. (544,500 nanoseconds into milliseconds. You're off by a decimal.
I gotta go.
There it is. No, way too tiny. Way too tiny. I can't really see, but maybe. Is there a decimal out front there?
There's decimal after the third.
Then no. Times, what's that, 10 to the? No, too tiny. There it is. All right, so the correct answer here would be 0.5445 milliseconds. All right, so let's make sure that we can get this again. We're going to look at the metric prefix portion of our table. we're going to see that 1 nanosecond equals 10 to the 9 seconds. Remember, the 1 goes before the prefix. And then we see that 1 millisecond is 10 to the negative 3 seconds. So when we set it up, we're going to set it up 5,445,000 nanoseconds. We're then going to need to divide by nanoseconds, put that on the bottom. So then we're multiplying by 10 to the negative 9. If I stopped there, I'd have converted to seconds, but it wants me to go to milliseconds, so I'm going to have to do another one here that going from 10 to the negative 3 seconds is 1 millisecond. So punch that into the calculator, and my calculator gives me 0.5445. My units would be milliseconds, and then sig figs, I have 4 because there's no decimal in that number, so my calculator did me right. Okay? Again, the key part being making sure you're reading the table correctly. That's usually the step that people are getting tripped up on, right? And again, what's that one thing we're going to tell ourselves? The 1 before the prefix. That's how I make sure I'm reading that correctly. My 1 is always before that prefix, whether it's nano, milli, centi, kilo, doesn't matter. The 1 is always before the prefix. All right. Isaac, what's the next one?
I would say
Holy
holy moly for 400.
moly for 400. .045 pounds of helium into moles of helium. Yeah, so the easiest one is if you go out here and then go up these stairs. You're going to like go up the stairs, take a right, and then a left. And then what? That's not grams, though. So you're going to have to do one step first, is to get that into grams first. You got one too many digits. Yeah, look, 0.045 is 2. What's up? Yeah. All right, so this would be 5.1 moles of helium. All right, so this was a tough one, so let's see if we can make sense of this here. Pounds to moles here. So pounds is what? Volume, yeah, exactly, mass, right? And whenever we see mass and moles in the same problem, we're thinking molar mass. But the problem is the molar masses on our periodic table are in units of what? Grams per mole. So I'm not going to be able to use that until I can get this mass into grams. So first, I'm going to have to convert from pounds to grams. So I'm going to look on my constants page. I see that 1 pound is 450 something, 453.59 grams. So starting it out, 0.045 pounds of helium. Then I'm going to use the fact that 1 pound is 453.59 grams. Now I'm in grams of helium, so now I can use my molar mass from my periodic table. 4.003 grams of helium are in 1 mole of helium. Right, so 2 steps. First, I need to get to grams because that's what my units on my periodic table are. Then I can use my molar mass to convert from grams to moles. Right, in this case, I'm going to divide by that molar mass so that grams are on the bottom. Punch that into my calculator. I get 5.09906. My units are moles of helium. And then I'm going to round my final answer to 2 sig figs, which is how I get my 5.1 moles of helium. Okay? All right, Ed, give us another one. Isotope of dope for 400. Cool. All right, so 30 seconds here to finish this off. Yep. All right, selenium 79. What's that 79? The mass number. Whoops. Okay, and because it's selenium, that tells me that I can fill in which box? The number of protons, right? Because the number of protons will uniquely point me to one tile on this periodic table. So that means my number of protons is 34. So I can do my symbol, Se. The top is the 79, the mass number. The bottom is the atomic number, the 34. And what else am I going to remember to include in my symbol? The charge of -2 up there. the number of electrons, I'm going to have to use the facts. So these are these two formulas. Net charge equals protons minus electrons, and then mass number equals protons plus neutrons. So I'm going to have to use both of these to work backwards and figure out how many electrons I have. In this case, I'm going to need 36 electrons. And remember, I told you that once you get this number, take a step back and look at it. My charge is -2. Should I have more protons or electrons? Electrons. So this checks out, right? So it's just really easy to kind of mix those things up in your head. So just take a step back and look at your numbers, make sure it makes sense. All right, and then I need to figure out what adds on to 34 to give me 79, and that would be 45 neutrons. All right, 2, give me our next one here.
500.
Holy moly for 500. Going big. .7500 kilograms of ammonia into moles ammonia. All right, I'm going to give us 4 whole minutes for this one because this is a tough one. Yeah, nice. Is that last one a 4?
Oh wait, this is a 4 now.
4.04?
I need 4.
I think he went to molecules. So just moles. So not Avogadro's number. Yep. units. All right, so for this one, so first of all, answer is 44.04 moles of ammonia. All right, so first of all, I see that I have mass and moles in the same problem. So again, I'm thinking molar mass. I'm going to need a molar mass. But I'm going to need the molar mass of what? Ammonia, right? Which means that I'm going to have to figure out that molar mass first. The molar mass of NH3 is going to be the molar mass of nitrogen plus 3 times the molar mass of hydrogen. And so if you got your molar mass correctly, you should have gotten 17.03056 grams per mole. So that will help me to convert from grams to moles, but my mass is actually in kilograms. So the first thing I'm going to have to do is convert my 0.7500 kilograms into grams using that metric prefix conversion. Now I'm in grams of ammonia, so now I can divide by that molar mass, and I will be in moles of ammonia. So punch that into my calculator. My calculator gives me 44.03848. My units are moles ammonia, and I should have 4 sig figs, which is how I get to my final answer of 44.04 moles of ammonia. All right, Jenny, give us another one.
Okay. Covalent, schmovalent
Covalent, schmovalent for
for 300.
300. Oh, buddy, you are very lost. Oh. Yep. All right, so why'd you do that? Oh, I get it. Come on. All right, hold up. This thing's mad. There it is. So the name of this one would be selenium tetrafluoride. And then triphosphorus, so 3 phosphoruses, pentabromide, 5 bromines. Okay? All right, now we're going to do the big unit for 400 here, because I know everybody seems to be really pumped about unit conversions. $34.50 liters into quarts. That's good. You're close. I think you punched the number in your calculator wrong. So this is 36.46 quarts. Okay? So what's going to make this one tricky is there's no direct liter to quarts conversion on this page here. Right? There's nothing that will take me directly from liters to quarts. So instead I'm going to have to find a path. And that path is going to be to go from liters first to gallons and then from gallons to quarts. Okay? So I'm going to start with my 34.50 liters. I'm going to use the fact that 1 liter is 0.26417 gallons. So if I'd stop there, I'd have converted to gallons, but I'm going to do one more step using the fact that 1 gallon is 4 quarts. Punch that into my calculator, 36.45546. My units are quarts, and I'm going to round my answer to 4 sig figs. That's how I'm going to get my 36.46 quarts. Okay? All right, Stephanie, let's do another one. Covalent for 100. You have 15 seconds for this one. Yeah. All right, so CO2 is carbon dioxide, and then carbon monoxide would just be CO. All right, Amanda, pick another one for us. Big unit for 500, all right. 40.300 meters to feet. All right, again, you're going to need to find a path. And I'm going to give you a hint. Start working backwards from feet. Might make it a little bit more obvious. but off by some value. Look at how you punched it into your calculator. Yeah. Yep. All right, 132.22 feet. That's our final answer here. So this is a tricky one because there's no meters to feet conversion on here, right? In fact, I really don't see meters anywhere here except for angstroms, whatever the crap that is. That's definitely not going to help us, okay? But, so if we start working backwards from feet, I can see that I could take feet to miles. That's not going to help me. But I can go feet to inches, and from inches, centimeters. And do I have a way to get from meters to centimeters? I sure do. It's just at a different part of the table, right? So be careful. We can make any of these metric prefix conversions. So my path is going to be meters to centimeters, then to inches, and then to feet. Okay, and one other thing to sort of note here. This right here, centimeters to inches, that's the only jump from the metric system to the imperial system on this table. So if you're ever given a measurement in metric and want an imperial, somewhere, somehow, you're going to have to use that step. So I'm going to start with my 40.300 meters, and I'm going to use the fact that 1 centimeter is 10 to the negative 2 meters. Now I'm in centimeters, and I can go to my conversion page and find that there's 2.54 centimeters in 1 inch. And then finally, 12 inches are in 1 foot. All right, so that's my path to get from meters to centimeters to inches and finally to feet. Punch it into my calculator, 132.2178. My units would be feet, and then I'm going to round my answer to 5 sig figs. So mark that place there. That's how I get my 132.22 feet. All right, let's practice our ionic compound nomenclature again. Let's do ion nomenclature for 300. That's a 6. VI is 6. I'm blind. What's that Roman numeral in the middle?
4.
Yeah. There it is. All right, so let's do this bottom one first. Cobalt 4 nitride. Again, when you're going to do these, you're going to make sure to write each ion with its charge, right? Do it the long way. So we can look at these charges and then play the cross game. Be careful, this is nitride, not nitrate or nitrite, right? Those 8 and 8 is our special polyatomics. This is just the regular old from the periodic table. So then I do my cross and I get CO3 and 4. For iron and chloride, iron lives where on the periodic table? Transition metals. So I'm going to need to make sure to include that Roman numeral. So I'm going to have to first figure out that charge using the fact that I have 4 chloride ions, all of which would total up to a charge of -4, meaning that there's +4 charge, and that all sits on that one iron ion. So iron 4 chloride. All right, Claire, give me another one. Holy moly for 300. 33.2 grams of sodium chloride into moles of sodium chloride. But not grams, right? Yep. 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 Nice. Point 0.0568 moles of sodium chloride. So again, I got mass and moles in the same problem. I know I'm going to need a molar mass. But I got a compound, so I'm going to have to calculate the molar mass by adding the molar mass of sodium to the molar mass of chlorine, which would give me 58.44274. So I'm going to start out with my 33.2 grams of sodium chloride, and then I'm going to divide by the molar mass. That would give me 0.0568080. My units are moles NaCl, and I have 3 sig figs. So I'm going to round my final answer to 3 sig figs, getting me 0.568 moles of sodium chloride. All right, who hasn't picked one? Li Ping, let's pick another one for me. All right, yes, ions, everybody's favorite. What's the end on that? Your second word? What's the ending? I just can't read it. Yeah, up on the word. What's the ending on that last one? Boss. Okay, 8. Okay. I just wanted to- You need the Roman numerals. Check your Roman numerals. That one's good. Yeah, that one's good. 8, you gave me nitrite. Yeah. You gave me nitride. This is nitrate. What's the 8? I think you're missing something in your formula. Precious N3N. Exactly. Not a 2 out there. Nitrate is -1. All right, so again, let's do the formula first. So I'm going to say cobalt, and this name is telling me my cobalt has a +4 charge. What is nitrate? NO3 -1. So first of all, remember, there are these polyatomic ions that we just have to know. There's that one assignment that was literally just there for memorization. It gave you the name, asked you for the formula, gave you the formula, asked you for the name. You can go back and take that assignment over and over and over again for practice, and it has every single one that we need to know built in there. Okay, so that's just a great way that you can just sit there and make sure that you know that. Take it a few times. You know, take it once tonight, another time over the weekend. Just make sure that you have those polyatomic ions down. And again, If you're taking it with your notes open, that is not going to help you even a little bit, because of course it's very easy to see what the charge on a phosphate ion is if you're looking at the correct answer. Right? So again, that whole quiz exists so that you can take it with your notes closed to try to help you remember these ones that we have to know. So I'm going to do this with my charges. I'm going to do the cross method. Since I have more than one nitrate, I have to put it in parentheses. All right, manganese lives where on the periodic table? Transition metal. So I'm going to need to figure out the charge on that transition metal. And I have to do it based on the charge of the phosphate ion, which is what? -3. So if you didn't know the charge on the phosphate ion, it makes it impossible to get the name correct. Right? A phosphate ion has a charge of -3, meaning my manganese ion is going to have a charge of +3. So manganese 3 phosphate. What do we got? Let's get one more. Annabelle, pick one for me. Big unit for 300. ATM to Tor. What the heck is that? Doesn't matter. We know how to do it. Nice. Yep. You may annotate it, but it is going to be blank when I give it to you. Yep. All right, so 41.0 torr. So I'm going to look on my constants page, and I'm going to use the fact that 1 ATM equals 760 torr. And we can note that this is an exact conversion. So then I'm going to start off with my ATMs. I'm going to then use my conversion factor, punch that into my calculator. I get 41.04. Whoops, should have finished that off. My units are torr. And then finally, I'm left with 3 sig figs, giving me 41.0 torr. All right. Now we are getting into final Jeopardy round here. Dun, dun, dun. All right, so these are going to be like the worst case scenario kind of problems here. A gallon of gasoline combusts in your car's engine to create 8.887 kilograms of carbon dioxide. How many molecules of carbon dioxide are produced by that gallon of gas? It's molecules, yep. Molecules, not moles. Percy, you were right. You just need one more step. Yep. Yep. Yep.
Who created Avogadro's mayonnaise?
Avogadro.
Yeah, but like how? Like how did he come up with it?
It's sort of defined as the amount of atoms that are in 12 grams of carbon 12.
Is it like an exact measurement or?
It's not an exact, it's a measurement. So there are sig figs associated with it. What's your times 10 to the? Yep. You way big. That's 1.26 molecules. It's going to be a way bigger number, right? So I think you're forgetting the times 10 to the.
Oh, I see it.
Yeah.
I see it now.
Like why carbage? Like why did you choose carbon?
It's not really so. Basically, you have to standardize stuff, right? So it was just a way of we're using grams. Grams, like all these units were used at some point and then underwent like a formal redefining. So they tried to take what used to be a gram and make it as similar to what the new definition of a gram is as possible. So for example, like the grams are based on the weight of this like literal like sphere of, I think it's uridium, or no, not uridium, indium in a lab somewhere, and they say that's what it means to be a kilogram, and everything else is based off that. So it was essentially just a way to standardize stuff. We're going to say however many molecules are in 12 grams of carbon 12, that's going to be a mole. And so basically all the units underwent like this really big standardization process. A second is defined as how long a wavelength travels in a given span. Like everything has a very formal definition, and it was kind of an attempt to make it as close to the loose definition that existed before it as possible. Yeah. All right, so this has got a whole bunch of different things going on. So again, the more complicated problems here don't use just one tool in our little toolbox, but multiple tools in conjunction, okay? So how am I going to go about this problem strategy-wise? I'm going to try to pick out some keywords here. And the first keyword that jumps out to me is molecules. Molecules lets me know I'm going to have to use what? Avogadro's number. That's the only quantity that we have that deals with atoms and molecules, right? So I got Avogadro's number. And Avogadro's number will allow me to convert between molecules and what? Moles. Okay? So that's not the only thing that I'm going to need, right? But I can get from molecules to moles. So now thinking about moles, and I have moles and mass in the same problem, then I'm thinking molar mass. And molar mass allows me to convert between grams and moles. But I don't have grams, I have kilograms. So then I'm going to have to do one more metric prefix conversion to get from kilograms to grams. Then I can use my molar mass to get to moles, and finally Avogadro's number to get me into molecules, right? So pairing a bunch of different tools that we have here. I'll say one other kicker is that this isn't just the molar mass of carbon, but the molar mass of carbon dioxide. So I would first have to calculate that, and that is 44.0095 grams per mole. So I'm going to start with what I have, the 887 kilograms, and I'm going to convert to grams using the fact that 1 kilogram is 10 to the 3 grams. Now I'm in grams of CO2, so now I can use my molar mass. And now that I'm in moles, I can finally use Avogadro's number. To get to molecules of CO2. And so, I just got somewhere I don't know how to. Okay. So my final answer would be 1.216. That's what it's going to be rounded to the correct number of sig figs times 10 to the 26 CO2 molecules. And so I actually looked up this data. That's how much carbon dioxide is produced by a gallon of gas. So every time you use up a gallon of gas, you are generating 1.216 times 10 to the 26 carbon dioxide molecules. Hence global warming, right? Speaking of, my ass has to drive 38 miles every time I come to work because I live all the way up in Coarsegold. So now we're going to do another tough problem here where we're going to have to use a bunch of unit conversions because you're going to convert 38 miles into kilometers. I will give you a hint. You are going to need 4 conversion factors in order to make this happen. So you need to find a path from miles to kilometers on that constants page. Oh no, it's going to be 5 actually. Sig figs. There it is. Yes. I don't know. It's going to be timed for an hour and 15 minutes. All right, so you're going to have to find a path from miles to kilometers. And it's going to take a bunch of jumps. We got to first go from miles to feet. From feet, we can get to inches. From inches to centimeters. Then to meters. And finally to kilometers. All right, so the final answer would be 61.2 kilometers. So 38.0 miles. Use the fact that 1 mile is 5,280 feet. And 1 foot is 12 inches. 1 inch is 2.54 centimeters. 1 centimeter is 10 to the negative 2 meters. And then finally, there are 1,000 meters in 1 kilometer. Punch that into my calculator. I get 61.15507. My units are kilometers. And then I'm going to round to 3 sig figs, giving me 61.2 kilometers. All right. All right, y'all. That about does it. Nice job. Way to stick with it.